So, on Monday, we introduced the notion of fundamental domain for a Fuchsian group. So then just recall that if I have a group acting on a set, a fundamental set for the action is a subset that contains exactly one representative from each orbit of the action. And also that a subset of the complex plane is a domain precisely when it's open and connected. And so for a Fuchsian group, a subset of the hyperbolic plane is called a fundamental domain for the Fuchsian group if it is a domain, and in between that domain and its topological closure inside the hyperbolic plane sits some fundamental set, which in particular tells me since in between there is some fundamental set, in particular different points in D cannot be in the same gamma orbit, right? Because if D is contained in a fundamental set, well, I know that this fundamental set contains exactly one element from each orbit. So two different points have to belong to two different points in D, then would have to belong to different orbits. Right? Okay, so in particular for a fundamental domain, different points always lie in different gamma orbits, or if you want, are not gamma congruent. And finally, the last condition is that the hyperbolic area of the boundary, of the topological boundary of D, be null, be zero. So that we introduced that notion. Now here you see I'm using the as I said that time as I said on Monday, I'm using this letter H just so that we are aware that sometimes I may take discrete subgroups not of PSL2R, which is iso plus re of u gu, but actually I may take discrete subgroups of PSU11, which is iso re dgd, right? And the point is that these two groups really are isomorphic as topological groups, right? Through an isomorphism induced by a Riemannian isometry of these two, right? By this Cayley transformation. But so my point is, I'm going to be considering sometimes discrete subgroups all in the group of Riemannian isometries of the Poincare disk, not only of the upper half plane. Right? So that's why I use the letter H, right? So that to be aware that I may be referring to either of the two models, U or D. Yeah, and then we started studying the so-called locally finite fundamental domains.
May I ask you a quick
question? Yes. Okay, and then we started talking about locally finite fundamental domains. And somehow the point is that one property we would like is that when we have a fundamental domain, that we can somehow, what we would like to be able to obtain this orbit space by simply considering the fundamental, the closure, the topological closure of the fundamental domain, and then performing some gluings dictated by gamma. Right? In other words, by simply taking the closure of the topological closure of the fundamental domain, and then identify points there that lie in the same gamma orbit. Kind of just in the same way that one can visualize R2 modulo Z square simply by taking the unit square and then doing this kind of the famous gluings. Right? So somehow we want something similar, but now for Fuchsian groups and for these fundamental domains. And then the question is, when doing this gluing actually gives me this space, that is when the natural map that always exists, when is it a homeomorphism, right? And we started seeing that the answer was that this happens, that this is a homeomorphism precisely when D is a locally finite fundamental domain, where here is the definition. So a fundamental domain is said to be locally finite if for any arbitrarily given compact set in the hyperbolic plane, the number of gammas that make D bar, the topological closure, overlap K is finite. Right? So only finitely many gammas take D bar kind of close enough to K. So somehow that's the point. Okay, and then here I also mentioned an important exercise, which is that. Maybe it's good that I somehow sketch the idea again. So suppose that I have my fundamental domain. Sorry, no, not the fundamental domain. That I have. Sorry about that. That I have a point Z0. Yeah, and then let's take any compact disk centered at Z0. Any. Right? So this one, and it's just any compact disk centered at Z0. And what I know is that if D is a locally finite fundamental domain, then only finitely many gammas have the property that the images of D somehow start overlapping. Right? So now on the other hand, I know that yeah, okay, so let me maybe start drawing those overlappings. So let's say that that's one by some action of some gamma that somehow I would draw like in green, and then this other one, and I don't know, a couple more. Let's say this, and then let's say just this orange one. Right. So what I know is that only finitely many gammas have this property that the corresponding images of D have overlapped my arbitrarily given compact disk. And now what I know is look, now focus on this compact disk, and what I know is that each point inside belongs to some gamma D bar for some gamma, right? And that is simply because D bar contains a fundamental set. That's one of the conditions of being a fundamental domain, right? That in between D and D bar sits some fundamental set. So any point here is gamma congruent to some point in that fundamental set, hence some point in D bar. So you see somehow what I drew, which is somehow that with these images I really somehow managed to cover the whole disk. Is that picture is accurate, right? Because every point lies in some image in some image gamma D bar. Okay, now and I know that there are only finitely many such regions, right? And of course, as it's depicted here, some of these regions may fail to contain my original Z0. It may be that Z0 is in several, right? I mean, it may be that something like this happens. Let's say, I don't know, here it is in red. I don't know, let's say, yeah, that my point Z0 is in two gamma D bars for different gammas. That may perfectly happen, but it may perfectly happen also that it is outside some of them. Right? So like this one, and this one. So something that I can do is since I know that these are finitely many, and they are all closed because they are images of this closed set, what I can do is I know that there is some small enough radius with the property of not intersecting any of these images that didn't contain Z0. Right? So for this new smaller compact disk, what do I know? I know that again the number of gammas that make d bar overlap it is finite. But now I know that for any that whenever a gamma has the property of making d bar overlap it, Z0 automatically belongs to that gamma of d bar, right? By construction. And so that's what the exercise asks, and I pretty much solved it. Yeah, and this is going to be important. So somehow we can find R small enough so that whenever this one overlaps the compact disk, it does it because Z0 was already there. And this is for each Z0 I can find such an R. Okay, and then the main theorem is that here this iota bar is a homeomorphism if and only if this is a locally finite fundamental domain, and I did this proof, this implication, so that if it's a homeomorphism, then D is locally finite, and then I was in the middle of the converse when I ran out of time. So let's now start with this. So let's suppose now that this is locally finite, and I want to see that then iota bar is a homeomorphism. Now something which is easy is what is easy is that it is continuous and that it is bijective. That's easy to prove. So somehow we are only left with showing that it's an open map. That an open here always is always mapped to an open here. So I take an open here, which is this A, and then since it's an open in this space in which I put the identification topology, what I know is that, well, actually, just because of surjectivity, well, in any case, that the preimage of A is an open set in D bar, but in D bar, I use the subspace topology. So this open set, the inverse image of this open set, under this projection. So let me go back under this projection. So A is here, and then pi inverse of A is here. Yeah. So this open set, since in D bar I use the subspace topology, this one has to be of the form the subspace intersect an open set in the big space. Right? So I express it in those terms. Right? So D bar intersect an open set of the big space. Right, and now I consider this one, right? So this is an open set in D bar, right? But it's kind of an open set in D bar, but somehow I really don't know that it's an open set in H, right? And somehow, look, I want to produce some open set in H, right? Because now I'm here with this D bar intersect B, which is the inverse image of A under pi. And somehow I want to move here, so I want to see that I would like to produce here an open set that somehow is mapped by P to the same set that this one is mapped under P. That's what I want, right? So that when I instead of traversing this way, I traversing just this way, the image of A under iota is open. Now D bar intersect B, that it may fail to be open in the big space. But so what I do is, since I'm interested in projecting back to H modulo gamma, to the hyperbolic plane modulo the action of gamma, what I do is I look at all the images of this one under gamma, right? Because you see P of this set is equal to P of this set, right? Because P of a point is the same as P of any element in its orbit. Yeah, and somehow, although this may fail to be open, somehow I claim that this one is open in the big space. Okay, and so now I start the quest to showing that this union is indeed open, so that this is open. And so take any element here, so that I'm going to take any point in one of the sets whose union I'm taking. So I take one of them with this gamma and a point in that corresponding member of the family. Yeah, and then I go back to D bar, right? Because Z naught is in gamma of D bar intersect B. So I just take gamma inverse of Z naught, just to move back to D bar intersect B, which is where I have control, where somehow pi is defined, right? So that's why I want to move back to D bar using gamma inverse. And then by the exercise whose solution I just sketched, I can find around this W naught, I can find this small enough R with the property that whenever an element of gamma makes D bar overlap the compact disk, then that was because W naught was already there. Okay. And now I notice that, so notice here in S, in this set S, I'm considering already all the possible elements of gamma that make this one overlap this one. Right? Now, every element of here is in some overlap, because every element here is in the gamma orbit of some point in D bar. So every element here is of the form nu of some point in D bar. So every element here is in some of these overlaps, and here I'm already considering all the elements of gamma that make up an overlap possible. So this means that this set is in the union of all of this, with nu running in S. Okay, and in particular you see the finite, right? So somehow this compact disk is contained in the union of finitely many images of D bar. Okay, now let's number the elements of S. Let's say nu naught to nu m. And starting with the identity, I mean, of course, the identity, you see, since W naught is in D bar, of course, the identity has the property of making just D bar overlap this one, because W naught is there. Okay, so I start with the identity, and okay, I number, and then what I see is that because of this property, what I see is that you see W naught is in nu zero inverse of D bar. W naught is W naught is in nu zero of D bar. W naught is in nu 1 of D bar. W naught is in nu 2 of D bar, etc. And so I can just apply to all of that. I can to each of those belong relations. I can just apply nu inverse, and what I obtain is that nu naught, nu one inverse of nu naught, etc. They are all in D bar, right? It's just this condition, but with a nu inverse of nu naught, then in D bar. So all of these points are in D bar, and that means that we can apply pi to each of them, right? Because recall that somehow this pi is really defined only in D bar. So outside of D bar, I cannot really speak of pi of something outside of D bar. But these points are in D bar, so I can apply pi to each of them. And well, notice that all of each of these, you see, this one is in the same gamma orbit as this one, in the same gamma orbit as this one. So they have to be glued, right? The pi of all of them is equal. So pi of W naught is equal to pi of the next one, blah blah blah, to pi of the last one. And now Z naught was here. So you see Z, how to say, just 1 second. I want to justify that all of these are in A. Yes.
Maybe.
Yeah. So these points may not be the same.
Yeah.
They may not be the same because they are in D bar, not in D, right? So in D bar there could be different points. Yeah. that are gamma congruent. Yeah. But you see, so in this space, what do? I identify whenever 2 points here belong to the same gamma orbit, I identify them. Right? Yeah. So, and then these ones are clearly all in the same gamma orbit.
Yeah. Okay.
Yeah? I mean, they are in the gamma orbit of W naught, right? And they belong to D bar. I have to identify them under pi. Okay. Okay, so their images are all the same or equal. And now I want to claim that they are all in, that all of these are in A. Yes, sorry. Oh, okay, so this was obvious because W naught is in D bar intersect B. Yeah, sorry. And so in particular, W naught, pi of W naught is in A, and then it's equal to the rest. Then okay, then that point is in A. Okay. Now, but then I mean somehow that all of these are in A. Somehow that means that you see W naught is in B. Well, this we already knew, right? But then also nu inverse of W naught is in B, etc. All of them are in B. Okay, because you see, so how did I take B? What I did was take the whole inverse image of A under pi, and that one express it as this one intersects some open set. So here it's already how to say, whenever a point is here, and then I go under pi and then take inverse image, all these other points are here because this one is closed under the inverse image. So since all these nu one inverse of W naught, etc., they are all projected to the same point. They themselves are in pi inverse of A. Right? If you want to, that's the kind of just the easiest way to see it. So they are all in pi inverse of A, which is the intersect B, D bar intersect B. And then from that I see that, you see, I just consider, you see, I kind of forget a little for a while about this, and all of those are elements of B. So now I can start seeing W naught being an element of B, and then W naught being an element now of nu1 of B, etc. Right? Just apply the corresponding nu. Okay. Right. Now, B is open in U, right? I mean in the hyperbolic plane, and the nus are all homeomorphisms. So nu1 of B is open in U, etc. This one is open in U. All of them are open, and they are finitely many. So there must be some small enough radius, some small enough open disk around W naught contained in all of them, right? Because W naught is in all of those open sets, and they are finitely many. So a small enough open disk is contained in each of them. Okay, so I arrive at this, and so what I obtain, you see here I just kind of play with some basic set theoretical operations, right? Like so, because now I remember, you see, I remember this, that this compact disk was contained in this union, right? And then here you see this is the compact disk of radius r, and here I took the S small enough, you know, like even smaller than this radius, so that this open disk is actually containing this compact disk. And so also for this open disk, I have that this one is containing this union, and so it's containing this union and in this intersection. So it's containing the intersection of the union and the intersection, right? And then I start just playing around, right? Like it's a union intersection something, so I can just say take the union of the intersects, right? And then this intersect I can just like you see, I can just make it redundant, and then once I'm here, I notice that I can just you see, this nu k is bijective, so it opens intersections. So I can say nu k of this one, and once I'm here again, it's the same nu k for all the j's, so it can be taken out. And I notice here that, you see here I'm taking an intersection, but one of these sets is precisely when j is equal to k. So this intersection is contained in particular in that set when j is equal to k, which gives me this one. And at what I have arrived at, you see, this open disk is contained in the union, in this union of sets of the form I wanted, right? Like gamma translates of D intersect B, of D bar intersect B. So, sorry, and then also when I apply, sorry, there was one more step missing, because what I wanted was around Z naught, I wanted an open disk, and here what I have is just an open disk around W naught, not around Z naught. So I still have to apply in gamma, the gamma that I have fixed here. Okay, yeah, sorry, I was missing that step. So I applied gamma, and what I obtain is just, you see, I apply gamma to each of these, and now here these ones are all of the form I wanted, right? So, and this is an open disk, right? Because gamma is isometry. So this one is open. So it's open, and as I said, I mean, this one is really gamma stable, right? So it coincides with P inverse of its projection. So recall that here, this is the projection here, right? And if a subset here is gamma stable, then projecting and then taking inverse image gives me the same, right? Because if it's closed under the action of gamma, you see it already, and it has a point. It already has all the points in the inverse image. Okay. And so we see that this one, then you see this one has its inverse image an open subset of U. So this one is open in H modulo gamma, because in H modulo gamma we put the identification topology, and the identification topology is that its open sets are precisely those whose inverse image is open. So this one is open, okay, and then you see it's P of taking this one and kind of closing it under the action of gamma. So it's just P of the original one. And now P of this subset of D bar, you see, P of something that is already in D bar, well, it's iota P of the subset, and this diagram commutes. So P of this subset is P iota of the subset, and the diagram commutes. It's iota bar P of the subset. And this, you see, this P of this one was A. Right? And that's just because pi is surjective. You see, pi is surjective. So when I take an inverse image and then I project, and then when I take pi of pi inverse of A, this is A because pi is surjective. So, right, so this one here is A, and you see what I obtain is that iota bar of A is open in U modulo gamma, which is what I wanted, right? Because I started with an open set, with my open set A in D bar modulo gamma here, and I wanted to show that its image is open here, because that was the only thing missing in order to know that iota bar was a homeomorphism, because I already knew it's bijective and continuous. Okay, so yeah, so it has to be a homeomorphism, and then we are done. So the proof is kind of heavy, right? But at least it tells us something, right? If you compute a fundamental domain and it turns out to be locally finite, you can do the trick that we always do for R2 modulo Z square, as I said before, right? That you can just visualize it as taking a kind of a square, which would be a fundamental domain, which in that case is also locally finite, but then just glue, right? So for locally finite fundamental domains, that's the point, that we can obtain this space by simply kind of cut and paste in a way. Right? Okay. Another useful.
May I ask you a
Yes.
question?
Yeah. Okay. So we haven't. We still have to of course to answer the question of whether every Fuchsian group admits locally finite fundamental domain, and how, if so, how to compute, etc. But the intention is to give some answer. Yeah? But in the meantime, let's prove this which is actually useful, which pretty much says that if one has a locally finite fundamental domain, one can use it somehow to recover the whole of gamma. And how? Well, you see, you look at d bar, look at the topological closure in the hyperbolic plane, and then you see it's kind of it's something, right? I mean, so let's say maybe other color. Yeah. So yeah, so let's say that this is D, right? And then I mean D bar with the boundary. Yeah, I don't know. It's too ugly. Yeah, okay. And then somehow if you take any sorry, this is D bar. Okay, and now if you take any point in gamma, well, if for instance if it's any element of gamma, for instance if it's the identity, well, the identity doesn't move it at all, right? It doesn't move any of its points. But then some element different from the identity moves it, right? And then it may move it far away, I don't know, or it may move it not very far away, right? So that there's some overlap with itself, right? Of course, the overlap cannot be in D, because in D different points are not gamma congruent. So kind of the overlap is somehow in the boundary, but it could be that somehow in the boundary there's here with some image, right, of D bar. And then there are some certain, I mean, I don't know how many, but the point is that I can start just looking at those gammas which don't move this one very far away. So those are these ones, and the point is they generate the whole group gamma. So if looking at D, I just look at those gammas that don't move D bar very far away, then I generate the whole gamma. Okay. So let's prove it. The proof is actually not too long. I would say it's actually a nice proof. Yeah. So notice for each z, yeah, for each point in the hyperbolic plane, there is some gamma that takes it inside D bar, because D bar contains a fundamental set. Okay, so in other words, for every point in Z, there is some representative of its orbit that lies here, because here there is some fundamental set. And moreover, if two elements of gamma, see, if two elements of gamma take Z inside D bar, then the following happens. So consider gamma of Z naught. Sorry, gamma 2 of Z. Gamma 2 of Z, of course, is equal to this, right? Kind of just introducing this identity, this artificial identity. Right, and then what I can see is that gamma of Z naught is in D bar. Right? So this point is in D bar, but is equal to this is equal to the image under this element of this point, which also belongs to D bar. Right? So this point is in the image under this of someone in D bar. Yeah.
Should there be
Yes, thanks. yeah, so this point is in this intersection, right? But then you see then this composition has then the property of, so that it has then the property of making this intersection not empty, because then I can find this point, right? So if two elements of gamma take my z inside the bar, then inside this intersection I can find a point. And so this one satisfies the property that defining gamma naught. So this one then belongs to gamma naught, but then you see yeah. Then I have this equality. So 1 second. Yeah, sorry. I want to say that this coset is equal to this coset, but I don't know that gamma naught is a subgroup. But so you see, I just take the subgroup generated by gamma naught. Right. Yeah. Do you agree? Yeah. Okay. And then I can take that. Yeah. Okay. Okay. So and then here again, subgroup generated. Yeah. And so, but so you see, this means what does it mean? That it doesn't matter which element of gamma I take that sends z inside the bar. It doesn't matter. I always have the same coset of the same coset in gamma of the subgroup generated by gamma naught. So maybe the assignment z goes to gamma of z. That's not, sorry, z goes to gamma. That may be not well defined, but z goes to the coset of that gamma. This one is well defined. Yeah. And so what we have is a well defined function that to each point it sends it to the coset, to that coset where gamma is any element of the group gamma with this property.
Why is it well defined again? Sorry.
Yeah. So you see, so for this one, there is always someone who takes it inside the bar, and you see, but there may be many. Okay, but every time I take two of them that send z inside the bar, I can produce some reasoning that ends in those two elements belonging to the same, having the same coset. Yeah. So the assignment that to z assigns that coset, that one is well defined, because it doesn't matter. You see, I can use any element taking it inside the bar, and they all give me the same coset. Okay. Now, as the exercise that we did there yeah, sorry. Okay. So I have a well-defined function here. Now for every point in U, there is one small enough r with this property that I've been speaking from the beginning. That when I take this sufficiently small r, every time a nu makes this one overlap this compact disk, well, it's because z was already in the overlap. It was already there. Right? Somehow that the overlap is not peripheral, it's really kind of central. Okay, so I know that such R exists. Right. And now take any point, but not in the compact, but kind of just in the interior. So in the open disk. Yeah. And then for that W, of course, I can pick some eta in gamma that takes it inside the bar. Of course, I can do it. But you see, then when I consider eta inverse, you see, eta inverse of this point is W, which is here, and is also in eta inverse of d bar. Right? So I mean, this point is in d bar, so eta inverse of this point is in eta inverse of d bar, and so what I have is that W belongs to the intersection here when instead of nu I write eta inverse. But that means that eta inverse is in S, is in this set. Right? So in other words, this eta inverse satisfies that this overlap, that the overlap is not empty. But that means that Z is in eta inverse of d bar. So Z is in eta inverse of d bar. But then you see eta of Z is in d bar. Eta of Z is in d bar. And what does that mean? That means that phi of W, which is this coset, right? By definition, phi of W is the coset of the one that does the job, right? Of the one that does the job, right? But the one that does the job for W, but the one this one that does the job for W also does the job for Z. So this one is also phi of Z. So what do I get? That in this open disk, phi is constant. So as a function defined on the whole U, phi is locally constant. Okay, but U is connected, so phi has to be constant. Okay, so phi is constant. Now, of course, phi is surjective. Right? I mean, of course, right? If you give me this is not in D, this is in gamma. If you give me any point here, any element here, so it's the coset of some gamma, right? Of course, this one, you see, whenever I take any point in d bar, I can write that point as gamma of this thing, which means that the coset of gamma is phi of this one, right? Because gamma does the job for this point. So phi is really obviously surjective. And here is again coset here of the subgroup. Here again. And so you see, what do I have? That this function is locally constant and surjective. So the target cannot have more than one point. If it had 2 points, then by surjectivity there would be a constant function with 2 different values. So that's impossible. So this has to have only one element. But having only one element means precisely that this subgroup is just the whole thing. Okay, so that's something kind of a useful feature of locally finite fundamental domains. Yeah, and then the question, right, that I mentioned before, which is, does every Fuchsian group admit a locally finite fundamental domain? And the answer is going to be yes, and at least conceptually not hard to find. Yeah. Okay. So for the definition of the Dirichlet polygon. Right? So I start with a Fuchsian group, and I take an element, a point in the hyperbolic plane, which is not fixed by any non-identity element. So in other words, I pick a point which is not an elliptic fixed point, so that its stabilizer, only the identity, stabilizes it. And here it's important to recall that we proved that the set of elliptic fixed points of gamma does not accumulate in the hyperbolic plane at all. So it really, if you pick at random a point in the hyperbolic plane, it is most likely one of these W's. And if it is not, then you know that if you move a little bit, then you have one. Yeah? So somehow my point is that such W's, there are a lot of such W's, and somehow they are not hard to pick. Okay. Now, for each non-identity element, I'm going to define these two sets. So this one L gamma of W, right? So I already fixed my point W, and it's the set of all Z's that are in the mediatrix, in the hyperbolic mediatrix between W and gamma of W. Right? So you see for this one, somehow let's say drawing only a sort of Euclidean picture. If this is W, let's say in green, if this is W, and let's say that here is gamma of W, I want the points that are equidistant from W and gamma of W, right? So equidistant from here and here. So for instance, if we were speaking about the Euclidean plane, it would just be the mediatrix, right? So okay, so that's but now we do it in the hyperbolic plane. So this is some set, right? So I don't know exactly how it is, at least for now, I don't know exactly how it looks. But what I know is that for any point there, this hyperbolic distance and this hyperbolic distance are the same. Okay, now H gamma of W, and what I do is, you see, now I consider all the points that are closer to W than to gamma of W. So in this picture, it would be like all those that are here on this side. So at least it looks like half, right? Like half the plane. And of course, this one, since gamma itself is an isometry, of course, I can here in this number doesn't change if I apply gamma inverse to both. So this number doesn't change. So of course H gamma of W is also equal to the set of all Z's, with the property that Z is closer to W than the image of Z under gamma inverse. So you see, it's kind of slightly, the picture is slightly different from this one. Right? So this one is all those sets, the sets, so that this distance, somehow this one is smaller than this one. But this somehow, although the set doesn't change, somehow the meaning is slightly different. It's the set of all Z's with the property that whenever I apply gamma inverse to Z, so that I obtain some other point, this distance is smaller than this other distance. Okay? So somehow the set is the same, just the property has a slightly different meaning. So that gives us some flexibility. That's going to give us some flexibility. Okay, and you see, somehow with this h gamma of w, somehow what we are doing is, for this element gamma, we are somehow trapping this w, right? Trapping this w with this mediatrix L gamma of w, so that we consider only this part, and somehow that's the whole idea. So what we do is we start trapping w with those sets, and then consider the traps for all possible gammas. That's what we do. And so the Dirichlet polygon is this intersection. Right? So the intersection of all these kind of half spaces. And then some exercise. I mean, it's not so hard, but one is that this one is actually well behaved. It cannot be any kind of, it cannot be very kind of a chaotic curve, or I mean, it cannot be like completely disorganized or meaningless curve. It's actually a shortest curve, right? And not only that, it's orthogonal to the shortest curve, joining them. Yeah, so yeah, I think, for instance, to try to prove this exercise, I would say one would try to find some hyperbolic reflection that interchanges these two, so that somehow one finds that precisely this one is that the mediatrix is the set of fixed points of that reflection. Right, yeah, so that's what I would do. That you see, kind of to prove this one, to start with what one wants to prove somehow. You see, want to start with this shortest curve segment, and then at the middle point, draw the shortest curve which is orthogonal to it, and then with respect to that shortest curve, which would be a straight line in the hyperbolic plane, define a reflection. Just take the reflection along that one, which then would send this one to this one, and then somehow and then this one is the points in this shortest curve would be all fixed by the reflection, and then you arrive at the fact that then it has to be the mediatrix. It has to be this geometric locus. Somehow, yeah. So somehow, and the point is, okay. So given a shortest curve, how do you actually define a reflection along that shortest curve and show that it's unique? Okay. I mean, in the end, one can state everything just in terms of the reflection that we already know, which is the reflection along the positive part of the imaginary axis. Okay. Another property which is not hard is that these h's, which are like these halves, right? So I have my L gamma of W here, and I have the H here. That one is convex and open. That's also not hard. And then some more properties. I mean, these are easy properties. Some sort of kind of reflectivity property, right? That this one is here if and only if the other one kind of some sort of reciprocity property, and so on. Now, yeah. So what else do I want to say there? Yeah, maybe about yeah, about 8 and 9 I want to say something. You see, for any sequence of pairwise distinct elements of the group, I really have divergence from W. This somehow, I mean, the distance really goes to infinity. And this 8 is really not hard, because if I have my W, if I have my point W, and if this were not true, then there would be some sequence of pairwise distinct elements of gamma, with the property that the distance doesn't go to infinity. So somehow that just 1 second. Yeah. Okay. So that it goes to infinity means that for every big enough open disk, there is some index n, with the property that beyond that index, all of them are outside. Right? If this were not the case, that it goes to infinity, then there would exist some radius with the property that it doesn't matter how far in the index you are, you always have a point. You always have some point there, right? And so there would be an open disk with infinitely many elements of this form. But then in the closure, the closure would be a compact disk, and there would be an accumulation point. Or okay, so there one has to be careful. Either there would be an accumulation point, or the sequence there becomes stationary, but then that means that the stabilizer of W is infinite. But in either case, I would be contradicting the fact that gamma is Fuchsian. It would be because I would have that either the orbit accumulates, or the stabilizer is infinite. Okay, so this is indeed the case. If you give me any sequence of pairwise distinct points, this distance goes to infinity. And using this, one can prove this 9, that for any compact set, the number of gammas that make the number of gammas for which this one intersects the compact set is only finite, and that is because if you give me I have W, right, and I have the compact set, which I don't know, a priori doesn't have anything to do with W, right? So but I have my compact set. I don't know, it could contain W or not, it doesn't matter, but the point is that when you see that there is some disk there is some open disk with center W containing K, because K is compact. Okay, and then And then somehow inside this open disk, there are only finitely many of these points, because this distance goes to infinity. So in other words, most of these points are far away from this disk. But if they are far away, you see the L's are also far away, because these are kind of equidistant. So as these points move away, the mediatrix between the point and this one also moves away. So for only finitely many gammas can the corresponding L gamma of W intersect my compact set. Is it clear enough or not?
I have a little trouble with
Okay. I mean, at least, okay, let's say, yeah, the point is that this argument that I gave is really not formal, right? It was kind of just kind of an intuitive argument. So that may be the reason of, I don't know, but at least I would like that intuition is kind of clear, and then we can discuss the kind of the formal proof later. Yeah. All right. Okay. And so example, right? So somehow the only interesting Fuchsian group that we know so far, which is PSL2Z. I mean, we know so far right now we don't know many Fuchsian groups. Right? We still don't have Poincaré's polygon theorem, which is a machine to produce new Fuchsian groups. We know very few Fuchsian groups at this moment. But so this one is kind of the most interesting amongst the Fuchsian groups that we know so far. So let's compute a Dirichlet polygon. Of course, the Dirichlet polygon is centered at a point, right? So of course, here, if I pick a different W, of course, I should expect the Dirichlet polygon to really change. Okay, and then somehow the claim is that this polygon P that you are seeing here, this open polygon here is the Dirichlet polygon for PSL2Z based at any IV, you see, above I. Now, formally, what's the formal description of P? Well, it's the intersection, you see, it's the point of all the Z's in U with real part between -1/2 and 1/2, right? And with norm, complex norm, the usual norm greater than 1. So that would be the formal description of P. Okay. Okay, and then we claim that it's a Dirichlet polygon. So let's see. So of course, this the horizontal translation by 1, of course, belongs to PSL2Z, because this one, of course, has real entries, and its determinant is, of course, 1. Okay, and and let's say, yeah, let's just take this one, and let's see the bisector. I mean this one, this mediatrix between W and its image for this gamma. And so here I would have IV with V greater than 1, so it's some point here, and then translation to the right, which is gamma. It's around here, and then you see the mediatrix is precisely this the vertical Euclidean, the Euclidean vertical through 1/2. Yeah, and then for gamma inverse is translation to the left by 1. So for this same IV, which is my W, I translate here, and then the mediatrix or the bisector is this one. So the intersection of the bisectors, you see, for gamma and gamma inverse is this. Okay. That on the one hand. On the other hand, consider this one, which is you see this one. Let's see what I mean. This one is of course in PSL2Z again, right? And now let's just see like what type of transformation it is. So let's say mu square. So let's say yeah. So 0 minus 1 1 0 square is 0 minus 1 and then minus 1 0 if I'm not mistaken, right? So just okay, so 1 second, I'm doing it live. So 0 minus 1, yes, sorry, minus 1, and then 0, and then 0 and minus 1, right? Yeah, sorry, it's more clear if I just write the matrix twice. Yeah, right. So this one against this one, right? And this one against this one here. Yeah, so it's correct. But so you see, this means that then nu square, which is mu of the matrix, this one square, is the identity, because it's mu of this one, but mu of this one is the identity. Okay, so this means that this transformation is elliptic of order 2. Okay, elliptic of order 2, so it must have a fixed point in U, right? So let's compute fixed point. So it has to be the fixed point one has to be able to compute it by Z equal to the value of this at Z, which is minus 1 over Z, right? So minus 1 over Z, and so one must have Z square equal to minus 1, so it's I. Right, so I is the fixed point of this one. Yeah. And well, okay, fortunately we are taking, well, I mean, okay, I would have to show that above this one there are no more fixed points of elements of PSL2Z, but okay. Okay, but then this means that this one, you see, this one really is like a rotation of the hyperbolic plane around this point by 180 degrees. So for instance, the image of this ray here is this ray here, right? And then kind of the image of something like this is something like this, etc. Okay. In particular, you see, when I consider what I had already computed, which was the intersection of these two, so it was this, I see that really kind of this one is overrepresented, right? Because here I have the point I, and then like a point here is a gamma congruent with a point here, etc. So what I see is that I really only need half, and that for that I only, you see, and I take this. Okay. Anyway, the point is that here is IV, and then you see here is the shortest curve passing through both, and the rotation of 180 degrees around I, then takes this one around here, right? And it's rotation, I mean, in the hyperbolic sense, right? Not Euclidean rotation. But here, since this one is vertical, one can see that. Okay, it's really okay. I didn't want to say silly things. Okay.
I mean, it has to map to the same point if we were to apply the inverse, so it has to be
right. Yeah, exactly. Exactly. And now the point is, you see, here I have this shortest segment, yeah, and I know that the bisector for that transformation, which is the one which is this rotation by 180 degrees, has to be orthogonal to this one and passing through I. So it has to be this shortest curve. That's what I wanted to say. Okay, and then at what I arrive is that now when I intersect the three half planes, the three hyperbolic half planes that I found, namely when I consider gamma inverse, and nu, the intersection of all those three is precisely P. Because the intersection of the first two is this one, and then intersect, you see V is here, so intersect with everything that is up here is just this, which is P. Yeah. What I'm claiming right now is only that P is the intersection of H of gamma, IV, let's say, intersect H of gamma inverse IV, where gamma is this gamma, intersect H of nu, for this nu, IV.
So
yeah, and then you see this intersection is just this stripe, right? And then intersect this, it just gives me precisely P. But of course, if I start computing new H of other elements of PSL2Z, it may be that this shrinks, right? Yeah, and that's the point, that we have to show that not. Now, but what we have so far is that this one is the intersection of all of them. It has to be contained in P. Okay. Now I want to show that it is equal to P. So suppose that is properly contained. So D is kind of, D would be some kind of smaller part of P. Right. And then, yeah, okay. So the point is that what I want to claim is that there is some point, there is a pair of distinct points of P. Sorry, there is a point in P. I have to say there is a point in P whose image under some other element there's some element different from the identity is also in P. That's what I want to show. From just assuming that this inclusion is proper. And what I would say is that we take that right. I mean, P is not closed. P is not closed. Right? P is open. P is not closed. And so and if we have this inclusion, then we also have this inclusion, right? Because if this inclusion is proper, then no, but then this may not be contained. Okay. What I want to say is that there's some point here not in the topological closure. Right. You see, let's say for a moment that I can manage to prove that there's a point here which does not lie in the topological closure here. Then what do I obtain? Then for that point, there has to be some element of gamma that puts it inside the topological closure. Because this one is a fundamental domain.
We know that already?
Right. We don't know that yet because I haven't proved it. Yes, you're right. You are right.
On the other hand, we are just looking at an example, so we're gonna show that
right.
later on, so
Yeah. But I also want that one to be in P. But then that would be easy, because then you see, if I take something here not in the topological closure, P is open, so I can take some disk, and then that point would be I would be in P here, right? Yeah, and so the image of this one would be somewhere in the closure, and then the image of all of this would be in the closure, but so somehow there should be one point that actually lands in D, and D is contained in P, and then I would have my statement here that there is Z and some element with the property that mu A of Z is in P. Yeah, but then of course this knowing that this is a fundamental domain already, right? Okay, okay, and I ran out of time. Yes, and now maybe let me finish. Why from this I can deduce that there is something here not in the topological closure, and it's because you see D PSL to Z, whatever, closure interior is D PSL to Z IV, and you see this. So if I just take this set, close it, and then interior, it's the original set because it's convex. So I'm also using that it's convex, but which is not hard because this one is by definition an intersection of convex sets. So, but because it's open and convex, I have this equality. So if P were contained in the closure, then P would be contained in the interior of that closure, so it would be contained here, in contradiction to my assumption. Right. Okay. So modulo proving some properties of some general properties of the Dirichlet polygon. Yeah, and then I have to continue. So let me continue then on Monday.